Now, if we have a density function, we usually, I've tended to use rho for, excuse me, as a symbol for density, but now we're into three-dimensional coordinate systems, and rho is one of the coordinates that we use in spherical coordinates. So I want to get away from any confusion that might be caused by using rho for the density before we actually get to spherical integrals when we have densities and spherical coordinates. So the density function I'm going to call delta. That's a Greek lowercase delta of x, y, z. If that's the density, then really all we need to do is look at that ijk block, that one little block in the stack of blocks between the x-axis and the sphere. We look at that one increment, and from that we can build up the whole integral. So the mass of the ijk block is what? Well, it's the density at the position of that ijk block multiplied by the volume of the block. It's density times volume. Now, the density function has to be evaluated at some point. At what point do we evaluate it? Well, that's why we have a sample point. We evaluate it at the sample point. Understanding that as the dimensions of the integral approach zero, the sample point gets the maximum distance of any point from the sample point within that increment approaches zero. So as the distance gets very small, if the density function is continuous, there's not going to be much variation of density within that tiny interval, so that we're going to approach a valid limit. Now that's a hand-waving explanation. You should be able to do it with epsilons and deltas, but actually I think the whole world's getting away from doing that in a first or second year calculus course. So anyhow, we should be moving in that direction, so you should think through that. Okay, so anyhow, we get density times volume is the density evaluated at that sample point, xi star, yij star, zijk. And if you see that there's a, I thought the I was missing because it's kind of sloppy, but I guess it really is there. There's the I, there's the J, there's a comma. It's hard to distinguish them. Anyhow, you evaluate the density at the xi star, yij star, zijk star point. Multiply that by the dimensions of that little rectangular solid, and you have the density of that region. Well, then we sum all the density, all the masses of the regions, okay, and that's what this sum indicates. Sum all from I equals 1 to n, j equals 1 to n sub I, k equals 1 to p sub ij, of all the delta m ijk's. Well, what do we get? Well, write out the expression for delta m ijk that we had up here, and put some parentheses around it, and we have a sum very much similar to the sum that we had when we did the volume. Let's put that up here just to take a quick look at it. We've got a precarious point of balance here. Let's see, are we stable? Not as stable as I'd like, but I'll just point to it and take it away. Remember, this is the sum we had for the volume, and of course it approached this integral. Well, this is the sum we have for the mass. It looks just exactly like the sum we had for the volume, except that we've multiplied within every increment by the density. And that's going to approach an integral with exactly the same limits we had before, because we're integrating over the same region. But we're going to end up with the density function within here. So that integral is going to give us the mass, assuming the density function is nice enough that we're able to perform the integration. Otherwise, we have to go to approximations. Okay? So, okay, that's all I'm going to say about this. I'm going to say a little more. What if we wanted to find a moment of inertia? Well, we'd have to find an expression for the distance of the xi star, yij star, zijk star point from the axis of rotation. because that would be the r of our mr squared, okay? So we'd have a delta m times r squared with that expression, so we'd have to insert the expression for r squared, okay? Now, what that expression might be depends on what axis you happen to be rotating about or what point you happen to be rotating about. But that expression would end up right in here with all the rest of them. So, these integrals are really ultimately pretty easy to set up. They might or might not be amenable to closed form integration.